Okay, so a DC motor has essentially the features of split ring commutators to change the direction of current every 180 degrees. An AC motor is a little bit tricky where we essentially have slip rings that don't change the current. And so with these particular devices, their spin has to orientate itself to the actual frequency of alternation of the current. So you don't find a lot of those motors, although there are some clocks that use the 50 hertz of household electricity to actually get their ticking mechanism to be quite accurate. However, AC motors are not very good. Now, a DC generator you saw before, and an AC generator where they use the changing magnetic fields to induce currents in different directions. What this particular this lesson is about is AC induction motors. An induction motor is not an AC motor. An induction motor does not have brushes. Brushes wear out. Brushes create energy loss. Brushes create sparking, which is heat energy, and light energy, sound energy. It creates ozone, which is a nasty smelling toxic gas. So what we want is a system which doesn't have brushes. It doesn't lose all this energy. And one of the best motors to do this is called the AC induction motor. A simple DC generator can be turned into an AC generator by simply changing the slip rings. Okay, so this we've seen before. So here we've got slip rings in here, we have the split ring commutator. DC and AC motors have the same changes. So an AC induction motor does not use any of these structures. It is entirely different in function. Okay, so be careful of your wording. In order to understand this, we've got to go back again, Faraday. So he states that the changing and moving magnetic field will induce an EMF. Lenz's law states that if an induced current can be produced, it will induce a magnetic field that will oppose the changing magnetic field that created it. Okay, so once again, don't forget that middle link, and we'll just keep repeating that until we go black and blue in the face. What if the changing magnetic field was created by an oscillating array of electromagnets? Okay, so, and I think it's on to the next slide on this one because it was just a short one. So, an AC induction motor has quite a unique design. Think of a rotor which consists of only a conductive metal material which has a high electrical conductivity sitting in the middle of a circle of, electromagnets. So imagine you have here a cylinder of iron. Okay, we know iron conducts electricity, and iron allows magnetic fields to travel through it. And the iron has little slits in it, of course, to essentially laminate it. Okay, we're going to call that a squirrel cage, and I'll talk about that in a sec. But if we have solenoids hooked up on the outside like this, okay, with the laminated soft iron core inside the electromagnets so that we don't lose all of the energy inside, we will essentially have a magnetic field that moves. How do I show you this? Well, okay, let's start with the inside, the rotor. The rotor is called a squirrel cage because it consists of a laminated metal cage. This device has the function of allowing induced current to flow while minimizing the production of heat. Okay, so what we actually want here is a system where a magnetic field will allow a current to be induced in this system so that a current forms and a magnetic field forms around each of these bars. But it's not a generator. We are talking about a motor. So we want electricity to travel through this cage, but we don't want eddy currents to produce heat. That would be inefficient. So the rotor is attached to a flywheel which spins the device, i.e. spins the drill. So essentially your drill bit, or your whatever component you're spinning, is attached to the rotor. Some squirrel cages are a bit more complex in design, yet act in the same way. Okay, so here is one that I found online with laminations and iron cores and a little bit high end. The squirrel cage slips inside the stator, remember stator, which has an array of magnets, very close but not touching. Okay, so this guy slides inside him, and that's how the structure of it fits. The stator consists of an array of electromagnets placed around the circle. However, they are coiled or wired out of phase. So, I hope this fits on the screen. What we have here is a colouring system to help show you what's going on. If the current was to travel up this blue cable, so let's grab a blue pen and just we'll say for a split second, for a moment in time, the current travels this way. So this blue coil is wrapped around, and you would use your right hand palm rule to say that this guy is creating a south pole. At the same time over here, because this is wrapped this way and the current is now traveling up this way, you would use your fingers, your right hand grip rule, to show that the magnetic fields are going out this way, and on this side you're creating a north pole. So these create essentially a plane with which magnetic fields act. And you could do the same with these coils up here. However, the coils are not all generating the same electric current at the same time. Instead, we're going to supply them with what's called three-phase power. A bit like how we generate AC current in a generator, you can produce three-phase electricity using exactly the same system. And we can use wave rectification here in substations to turn it back into regular AC for households. But what it means is that if you have a blue EMF being induced in one of your solenoids, your other solenoids will be out of phase by 120 degrees. So if you have three phases, all out by 120, they will add up to 360. So you can see here that this point to here is 360 degrees. And all of these particular fields all end up going through 360 degrees at this point here. When you plug in three-phase power to our setup, you get a crazy pattern. It's hard to understand. What are we looking at here? This is diabolical, Mr. Donald. What have you done to us? At one point in time, the current here is going to produce a north pole and a south pole. Over here, it's going to produce a north pole and a south pole. But here, for the red coil, we can see that at this particular point in time, we have none. So I've got a feeling that the diagram below you is at this point in time. The red coil has no magnetic field being produced. The blue one has a north pole on the left, and the green one has a north pole on the right. And so at this particular point in time, this is the field that you would get. Okay, so here is an animation I found, which sometimes helps and sometimes makes people cry. So let's run through it step by step. The little tiny dots on the outside here, they are the magnetic field created by these stationary solenoids. At any one point in time, this we can call, say, a south pole, and this we would call a north pole. So as this guy creates a north pole, he dies, then this north pole is created, this guy's creating a north pole, then the north pole dies, this guy's creating a north pole, then it dies, then this guy creates a north pole. I can go on and on. Essentially on the opposite side, because they're in phase, whenever this guy is a north pole, so if he's building a north pole, he's building a south pole. So you can see that they essentially align. And as one of these solenoids increases its north, it then will drop to 0. Then it will start increasing a south pole. Now, what does this mean? This here, these inside ones, are your squirrel cage. Your squirrel cage is just a piece of metal that allows electrical conduction. The currents can flow. So what happens here is we have Lenz's law. As a south pole is pushed towards this end of the squirrel cage, a current is induced. That current is the opposite direction because you want the magnetic fields to oppose. So as the south pole comes towards the squirrel cage, a current is induced in the squirrel cage, which creates a magnetic field to oppose this changing magnetic field. So the squirrel cage has a current induced in it, which always sits in front of the magnetic fields. If you want a north pole to stop coming towards you, then you create a north pole to push back against it. This is how an AC induction motor works. By inducing a current according to Lenz's law, if you move a south pole or a north pole on the outside, the inside magnetic field will always oppose this constant rotation. Remember, these magnets don't move. All they do is decrease and increase and create this overall resultant changing magnetic field. I hope your brains aren't totally dead from what I have just stated, but you did well.